The Curie temperature of nickel is 628.3 Kelvin and the saturation magnetization is 0.6 Bohr magneton per atom. Calculate the molecular field according to the Weiss theory. Your answer should be very large. Now, the magnetization M is equal to number of atoms per volume magnetic moment per atom times the Langevin field. So N is number of atoms per volume M is magnetic moment per atom. The Langevin function is cotangent hyperbolic alpha minus 1 over alpha, where alpha is in SI units given by mu0 permeability of free space mh, the magnetic field, divided by thermal energy kBt. And here the Weiss molecular field, if we combine the Langevin theory with Weiss theory, the Weiss molecular field is given by Hw gamma, the molecular field constant, times the magnetization M. And now we have alpha is equal to mu0 M, the Weiss molecular field, divided by kT, when the magnetic field is the Weiss molecular field, and this must be equal to combining with a Weiss theory here, substituting for Weiss molecular field gamma times M, mu0 gamma M capital M divided by kBt. So we can write magnetization in terms of alpha. Magnetization is kBt divided by mu0 gamma M times alpha, so it's linearly varying with alpha, and magnetization is also equal to capital Nm Langevin function. So we have two descriptions of magnetization as a function of alpha. So let's call this equation 1, this is equation 2. So these two equations should be simultaneously satisfied. These two equations should be simultaneously satisfied, and at the critical temperature, the Curie temperature, T is equal to Tc, we know that the only stable solution is magnetization equals to 0. So it has to be demagnetized, which means we should have the slope dm d alpha from equations 1 and 2 should be equal. All right, So we're going to equate these two slopes at the Curie temperature. So we have from the first equation KB Tc divided by mu 0 gamma m. So that's the dm d alpha at the Curie temperature from the first equation. And this must be equal to capital Nm, the derivative of the Langevin function dl of alpha d alpha, which is to be evaluated at the Curie temperature. And we know that this is capital Nm over 3 from the Taylor series expansion of the Langevin function. So we know that the Langevin function is alpha over 3 minus alpha cube over 45, etc. And the slope of the Langevin function is 1 over 3 for small alpha. So alpha much less than 1. Okay, so we can write the Curie temperature Tc as mu 0 gamma capital Nm squared divided by 3 kb. And the Weiss molecular field will be gamma times the saturation magnetization. So it's going to be gamma times Nm at that point. So this will be equal to 3 kb Tc divided by mu 0 m. Okay, so then we can calculate the Weiss molecular field. 3 times the Boltzmann constant, 1.38 times 10 to minus 23 joules per Kelvin times 628.3 Kelvin, our Curie temperature, divided by mu 0, 4 pi 10 to minus 7, times our magnetic moment, 0.6 Bohr magneton, 9.274, 10 to minus 24 joules per Tesla. So this gives us 3.72 times 10 to 9 ampere per meter, or if we find the B field, the magnetic induction, that is mu 0 times H, this is 4,674.6 Tesla. So it's a very large field. Okay, so what have we done here? We are looking at what happens at the Curie temperature to magnetization versus alpha. The magnetization as a function of alpha is given by the number of atoms per volume, magnetic moment per atom times Langevin function. This is our model of non-interacting moments in the paramagnet. That's the Langevin theory. Now the Weiss theory tells us that there's a Weiss molecular field which is related to magnetization gamma times m. So putting these two together, we find that the magnetization has a linear dependence on alpha on one side, and it is varying with the Langevin function on the other side. And these two equations are simultaneously satisfied at the Curie temperature at m equals 0. So the slopes of these two should be the same. So this is what we have shown in the lecture. And if we look at the two slopes, we see that kBTc over mu 0 gamma m should be equal to Nm times the slope of the Langevin function for small alpha, which is Nm over 3. So this gives us a Tc of mu 0 gamma and m square over 3 kb, and the Weiss molecular field that we will calculate according to Weiss theory, this will be equal to gamma times saturation magnetization, which is approximately equal to n times m. This is actually the zero temperature magnetization, but we can approximately take this to be n times m. So that gives us the maximum possible Weiss molecular field that we will see in this case. And this is going to be 3 kbTc over mu 0 m. Okay, so we can plug in the numbers here. So you can see that Kb is 1.38 10 to minus 23 joules per Kelvin. Tc was given, and our moment per atom was 0.6 Bohr magnetons. So this gives us 3.72 10 to 9 ampere per meter, or 4,674.6 Tesla.